Okay, so you all can see my screen on the chapter. So let me know if anything otherwise, all right? So we are going to actually move on into chapter 4. And chapter 4 actually describes the model and techniques for geometric modeling, okay? So this particular chapter actually will cover the entire modeling that you're actually doing in CATIA or any software for that matter that you're going to use, all right? So it deals with different types of models, okay? Basically, it's going to be discussing 3D models, methods for 3D modeling. But nevertheless, we know that when we were actually embarking on CATIA, we started with two-dimensional sketching and then we moved on into 3D modeling. All right. So basically, when we talk about the requirements of a geometric model, so what exactly is required in a geometric model? So it starts with, going back into what we learned in chapter 3, all right, where designing means, can someone tell me why do we design something? Anybody? Why do we design something?
To solve problem.
Okay, yes, to solve a problem.
To make our life easier.
All right, to solve a problem, to facilitate, convenience in our life, right? But the facilitation of convenience in our life is actually a particular problem that we are having, okay? So it would basically mean to generally solve a problem, and there is a need, so therefore we are moving into solving the problem. So when we want to actually, first we need to identify what the problem is. We have to identify the need to recognize the need to solve that problem, and then we come up with conceptual modeling. All right, so this is where the ideas come up for it. All right, we have the conceptual modeling, that means the ideas for the problems that you have identified. Okay, and from then we actually design something, we analyze, and then we move into the manufacturing. Okay, so for any of these things to happen, the geometric model must be there. So this is like what we call the center of our work, job, business, anything you can call it. So we learned in, someone's unmuted. So we learned in chapter 1, right? Model-centered engineering system. So this is where the geometric modeling is actually the model center over here. Okay, and then we move on into what are the functions of geometric modeling. So here, when we talk about the functions of geometric modeling, you see design analysis. So this analysis, we are not actually analyzing the structure itself, all right, as in the functionality of the structure. It's more like we are analyzing the model. So basically, this slide tells us what are the things you can use from your CAD environment. So for design analysis, as in the sense of analyzing the structure, we can actually evaluate areas, volumes, mass and inertia properties. Okay, we can check interference in assemblies, and then we can analyze tolerance build up in assemblies, and then we can also analyze if you have, like this kind of assembly where there's possibly any kind of mechanism where there is motion involved, then we can analyze the kinematics, okay, of movements between parts. And then after that, we can generate mesh for actually analyzing your model for its function, like finite element analysis. Okay, and then we have drafting. So in drafting, which is your drawing, what are the things we can actually check? Okay, so we can see automatic planar cross-sectioning, okay, automatic hidden line and surface removal. You can shade your images, dimensioning, create exploded view. So why all these things? Because we want to see and identify our model, interior, exterior, how the thing looks like in overall, right? So some of you might have experienced, like, when you I'm not sure if 2C did this, but 3C, they had to actually share what their model is with me for their mini project. So some of them just showed images of, let's say, an overall model. So when you show an image of an overall model, okay, I will not be able to see what's inside, right? So if I want to actually see, let's say they tell me we have about 20 parts, madam, then they have to show me, the exploded view, the cross section, then I'll be able to see the complexities involved inside, right? So there are many things you can understand from drafting. And then under manufacturing, you can classify your part, you can plan your process based on the type of parts that you have, and then you can generate the numerical code, all right, for manufacturing and generate your program, robot program generation. So basically this, when we talk about robot program, we talk about machining. And then when we embark into the production engineering, then we can generate your BOM table, okay, which tells us the number of parts, the quantity in each part, the description of each part, the type of material required for each part, and then the manufacturing resource requirement, and when we schedule our part based on the bill of material table, we can schedule, okay, when to bring in which material phases. And then we can go into inspecting and quality control. Okay, so inspecting and quality control is once your part is actually done. You have learned this in chapter 2, if not chapter 1, all right? Where the program generation for inspection machines, all right? When you have your part already created, we can actually, from the production, we can bring it to, let's say, the coordinate measuring machine and measure its, quality, coordinate, size, etc. And you can cross-check that with your CAD model. So these are all the functions under geometric modeling. So here we speak about geometric models, which we already covered in chapter 1. Remember, chapter 1 was some of the slides were actually a summary of all the other slides, all right? Sorry, all the other chapters. So there we discussed there are 3 types of models. So we have not 3 types of model. We had the initial 2-dimensional sketches, and then it moved into wireframe 3-dimensional, and then surface, and then solid. Okay. So here we are going to classify into 3 types of geometric models. Okay. So the 3 types of geometric models are the line, surface, and solid or volume. So what is a line model? A line model is a wireframe model basically, okay, 3D, where all the wireframe points are connected to create the image of your model. A surface model actually patches the wireframe only in the external surfaces. So there is no internal solid. And then the volume model is what you all are doing in CATIA. We have it broken into volume 1 and volume 2. Just a minute, huh? Just a minute. All right, okay. So this is what we are doing in CATIA. So we move on to the wireframe. This one I'll move a little quick because we've been through in chapter 1 itself. So basically a wireframe model, it gives you a visual presentation of the 3D physical object. Okay. And it allows you to enhance one step further from your 2D drafting system, which is only basically 2-dimensional. And you can actually start defining your entire model in X, Y, and Z coordinates. Like you would be able to do that, you can find what is the X, Y, and Z coordinate here, X, Y, and Z coordinate here. So basically it's 3-dimensional. So how do they actually come about? Like the concept is using like a metal wire to build. So like how children will, if you give them metal wire, they will twirl and, shape it into something. So the concept over here is the object is defined by a collection of points, okay, and edges. So points and edges connected together will give you a wireframe modeling system. So it uses geometric entities like lines, circles, arcs, so preset mathematical shapes. So here you have examples of wireframe. Okay, so because of this wireframe design, you can get a rough idea how the entire image of the product will look like. But as you would see, there are lots of ambiguity. It's very hard to define what is the internal and external part of this model. So the computer has no knowledge on the surface shape, okay, between edges on what is solid and what is not. So here you can see, you don't know whether this comes into the internal part or the external part. And it's always visually ambiguous. And then what happens is it tends not to be realistic sometimes, all right? And then complex models, they are difficult to interpret. Like this is a complex model, so it's hard to exactly interpret the dimensions. And then you can't actually decide information like mass property, volume, moment, and all those things in a wireframe model. And there is no guarantee that the model definition is actually exactly correct. Okay. So advantages, it's easy to construct. You can display quickly. It's very economical. Okay. Because, very fast you can sketch it. Like if I tell you what are you going to do for your mini project, you all can just sketch something. So very quick. And you can also draw impossible subjects because of the lack of logic present. Okay. So it's an example of wireframe. Okay. Now we move on into the surface modeling system. So it's a one step forward from wireframe model. So it is basically surface modeling is more of an aesthetic approach, all right, for complex surfaces. So it's essentially used to design like planes, ship hulls and all those things. So the aim with surface modeling is to completely define surface from an object, okay, in such a way that the computer can calculate the x, y, and z coordinates of the point on surface. So what exactly does this mean? That the surface helps you actually calculate x, y, and z coordinates. So this is what we are going to learn in the calculation part of this chapter, which I'll teach next week, or the next class, all right? So some surface, you cannot define them by analytical techniques like car bodies, ship hulls, die cavities, where the surface is so complex and curved, it's not relying on a particular mathematical shape or model. Now, what it does is you cannot define exactly, it could be, for instance, let's just say, okay, let's say you have a surface. So, it could be a combination of 1, 2, and then 3, and then 4. So, a combination of 1 curve, 2 curve, 3 curve, 4 curve, 5 curve. So, you don't know where the connectivity is, where the stopping point is, all right? So, when a surface, it just goes like this. This is basically a spline, okay, where if you extrapolate it into 3D, it becomes a surface. So, when it's very, very complex, it's very difficult from a coordinate point of view to identify what each of these points are, okay? So therefore, what we do is we use formulation to actually find out the coordinate points, all right? So how these surfaces are even formulated or designed within your software is using formulations. So how they model, they are modeled through a series of control points and other boundary conditions, which specify the nature and surface desired. So what they do is they use common polynomial methods, mathematical functions to actually design these surfaces. So you have things like Bezier surface, B-spline surface, NURB surface. So these are all mathematical formulations, all right, which is used to actually describe a spline or a surface. So we are going to actually do Bezier calculation with a spline in this chapter, okay? Otherwise, we have things like ruled surface, which you would have already seen in CATIA, where ruled surface is basically, when you draw a cross-section of something and you sweep it along a trajectory or you revolve it, one of those, okay? So the classification of surfaces, we have planar, which is actually plain, flat. So we have polygon, polyhedra, all those things. And then we have curved surface, where we have the single curve and the double curve. So single curve is like you see, we have a cylinder. Sorry, I'm actually using a mouse, so please pardon my extremely ugly sketch. So a single curve basically means from this top and this top, it will look flat, plain. And this entire surface is a curve, similar to cone, okay? So you have one flat surface and a curved surface. Now a double curve is like sphere, where you have one curve and then another curve, okay? So it's curved in both directions. So when it's curved in both directions, then after that you will have the like sphere, ellipsoids, paraboloids, and all those things. And then we have from the curved surface, the next one is we have the freeform surface, or we call it the Kuhn surface. So in the freeform surface, we use formulations like Bezier, B-spline, or whatever that I mentioned earlier on. So this is completely freeform, not related to any mathematical type of model, okay? So under the curved surface, single curve is one, double curve usually has ruled surfaces under it. And under freeform surface, we have lofted surface. So what is a lofted surface? It's a surface with multi-section solids. You will learn that as we come along, okay? So the classification of surface, sorry, the classification, just a minute. Okay, so the classification of surfaces is divided into 1 planar, 2 curved, and 3 freeform surface. So the type of curved surface, like a single curve, you can see these are examples of single curve, double curve. You can see the two curves are there. And then translation and revolution. So you would have learned this also, shaft, groove, and everything. Okay, so these are the surfaces. Okay, now that we classify the surfaces, the next would be to classify the resulting surface. So this was actually the classification of surface. Next, we will be classifying the resulting outcome of the surfaces just now. And that also is divided into three: generic, freeform, and derived. So what is actually generic? Let me change the pointer color. Okay, so what is actually generic? Basically, it's a general surface where it's divided into tabulated and revolution of surface. Okay, so tabulated is like the cylinder where you actually have your profile. Once drawn, you can actually sweep it along a generator curve, and you will get, like, let's say, a cylinder. Okay, or anything for that matter. Let's say you have this. Okay, this is a profile, and you have a sweeping trajectory, then you will get this, something like that. Okay, you have to really pardon my drawing for its extreme horrible outcome. Okay, so these are tabulated, okay, surfaces where you have plane and it is generated along a curve. All right. So the magnitude of a vector controls the size of the surface. Now, the next is surface of revolution. So the surface of revolution, basically, we are revolving. So let's say you have an axis, and let's say you have, like a circle over here. So if you revolve this, then you will get what we call like a donut-like shape. Okay, you will have like a donut-like shape over here. So basically, for a surface of revolution, you will be actually needing a cross-section profile. Can you close the door, please? So you will be actually having a cross-section profile, and you will revolve it around an axis. Okay, so this is basically surface of revolution. So the angle can be adjusted to 360, 270, whatsoever. So you all would have seen. So this is why I said this chapter particularly covers what exactly what you're designing in CATIA. Now, before I move on, just want to ask class 2C, where exactly are you all in your CATIA right now? Class 2C? Are you all there?
I think chapter 5, madam.
Chapter 5 is solid modeling. You all done sweep, pattern, all this already? Have you all done sweep or rib? Have you all done shaft, groove? These things done, covered?
Yes.
Yes, okay, all right. So that way you should be able to understand what I'm saying, okay? Okay, just a minute, just give me a minute. Okay, so this is surface of revolution. So as I said, so you'll see we've gone through this in CATIA, right? So these are tabulated cylinders. You can see you have a curve, and then this is your vector, okay? The trajectory of movement. Like this is a curve, and this is your trajectory of movement. This is the curve, and this is the trajectory of movement. Okay, and this is the surface of revolution. So you can actually do interesting things when you actually revolve something. Okay, the second resulting surface is freeform surface. Okay, so the freeform surface, it uses more than one curve to generate a freeform. Okay, freeform surface. So in this, there are five types of freeform surface. Okay, so the first one is the ruled surface, whereby you actually have two boundary curves. Okay, now using this web page, if I'm sharing, it doesn't allow me to on my video. So usually I try to show an example with a paper. Okay, never mind. So if you can just take like, an A4 paper or any paper, okay, your paper has 4 edges, right? 4 boundaries to your paper. We assume, of course, you have a normal rectangular shaped paper, right? So if you actually bend your paper just by imagining only these 2 boundaries, you'll be able to form a type of surface curve with that particular paper, all right? So which means your surface is ruled by curve 1 and curve 2. The next one is, let's just say you have your paper over here, which is a surface, which is ruled by 4 boundaries. And if you were to actually tweak each of this boundary, that means, bend this boundary one type, bend this boundary, this boundary, this boundary, you will notice you will get a type of ripple within the surface. So this is what we call a surface patch, which is enclosed in 4 sides or more sides, depending. Okay, so this is by boundary, okay, and this is by this is by 2 ruled curves, and this is by boundaries. The third type is a net surface, which is actually formed from a network of curves. That means you have multiple curves arranged, all right, in different direction, which actually forms the curve. And then we have the swept surface, where I told you just now, we have a particular profile against a particular trajectory. And then we have the lofted surface, okay, which is a surface cross section. So what is a lofted surface? So this is the one most of us would not have come across in our Katia yet. It is actually forming a surface. So when I'm speaking about surfaces, we can form a surface. Remember, everything that I mentioned can be also used to form a what we call solid, all right? So when we say a lofted surface or a lofted solid, all right, multi-section solid or blend, it simply means you are using different cross sections and blending them to create one solid. So you see here. Now, 3 different, let me erase this. Okay. Okay, 3 different cross section, okay. If I put a straight line as my guide curve, then what I would get, I hope, it will look like this. It will just look straight. Now, if my guide curve is actually curved, then you are able to actually guide the curve properly. So we will be able to see a better presentation of this actually in Katia when we are using it, all right? So the concept of loft, right? What is different is you are able to in one go, right? Mix different cross sections and blend them to build a solid. Okay. Like for instance, see, this is done through sweep. Sorry, not sweep, revolve, right? Where you are actually drawing the solid and then we are revolving them. Okay. So you could also use multi-section solid where you actually have one section here, 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 and then blend them with a guide curve. So that's also possible. And then the third type of derived surface is the common one, which is like the first thing is the offset surface. So you would have learned this from plane surfaces, right? From plane, offset plane, I taught the class, okay, where you actually have a surface and you just offset it, right, at a certain distance. And the other one is a fillet surface. Basically, all the rounds and the corners that we actually get, it is fillet, where between 2 surfaces, okay, what happens is we create a radius, or it's like taking a ball and sweeping it around, okay, to plan the fillet operation. So do remember, we have 3 types of surface classification, which is the plane, curve, and freeform. And then we have another 3 types of resulting surface classification, which is generic, freeform, and derived. Okay. So now we move on into Bezier curve. So I'm not going to cover Bezier curve today because I'll keep this for the next class. So Bezier, this is actually a small section of formulation, and why this is actually put into your syllabus. Of course, if you learn CAD in detail, it involves a lot of mathematical calculation, all right, on coordinates, units, and etc. So why we put in this Bezier curve, so that you can actually appreciate what is involved in just drawing a simple spline. What else to speak of complicated surfaces? Okay, so this entire calculation part we will go through the next class, right? Okay. Okay, so now I'm just going on to the application of surface, but then just give me a minute. All right, right. Okay, so now next we move on to the application of surfaces. So the application of surfaces, right? What are the usages? So basically, if you see design from then till now, you would agree with me that design has become more beautiful, right? Your whatever products that you have it's nicer, it looks better. Like right now, I'm looking at my computer screen, and right in front of me, the first thing that caught my attention was my speaker. Okay, so I remember speaker those days; they're just square and boxy in general. Now you have all kinds of speaker shapes. Then I'm looking at my pen holder. That too is just not a cylindrical pen holder; it has some kind of curved shape, and so on and so forth. And we can extrapolate as it goes. Okay, so basically, the application of surfaces, as I mentioned earlier, is for aesthetic purposes. All right. To create photorealistic images, right? And when you have different surfaces, due to the angle differences, you know, the color and, you know, light sources can actually enhance its appearance. But having said that, on the design perspective, it's not going to be something so simple. So the above characteristics makes surface a powerful industrial design tool to make your product more aesthetically appealing. So what is common and easily understood would be like our cars. You can see how our vehicles, you know, different surface design creates a very sleek and, you know, very classy, you know, very elite looking vehicle models compared to all these boxy shape models. Okay, so we went through wireframe, we went through surface, and now we are in solid modeling. So solid modeling is what we are dealing with, right? At least in this semester, in this chapter, in this subject, sorry. So what does a solid model do? It gives you a complete, all right, description of a closed and enclosed shape, right, 3D object, and it can be unambiguously defined, completely and unambiguously defined, right? So it's composed of combinations of primitive objects, complete, unambiguous, right, physically realizable and modifiable. And there are a few ways to actually identify a solid model. One is the constructive solid geometry, and the other one is the boundary wrap model. So what are these two? So what is a CSG model? So a CSG model representation uses a tree structure, okay, often called a CSG tree, to define a solid model part. So for the solid model, okay, we have a combination of solid primitives. We have, like, you know, different primitives like block, cylinder, cone, sphere, torus. So these are all solid shapes. The 2D equivalent will be like, you know, square, rectangle, arc, circle, like that. Okay, so we a circle made 3D, you will get a sphere. A rectangle made 3D, you will get a cuboid. A square made 3D, you will get a cube. So like that. Okay, so these are all solid primitives. These are the primitives used to mix and match in order to actually bring about another shape. So the Boolean operation is such that you use functions like add, union, subtract, difference, and intersection to cross combine to bring about a new model. So these are all the different solid primitives. And in a Boolean operation, so how is this done? Okay, before I speak about Boolean operation, it's for You can check with Dr. Alias. I'm not sure he's going to show this in the lab, but for my class, they will actually see this in the lab module. Yeah, let me see. Okay. Anyway, even if they don't, I've already attached a YouTube video over here on how you can view what Boolean operation is. Right. Okay. So basically, in a Boolean operation in CATIA, what happens is, you see, when you all are drawing, let's say I expect you all to draw this model in CATIA. So what you all will do, you probably just draw a cuboid, and then what you might do is you might round this corner. So the next thing that you might do is somewhere in the center of the plane, okay, you will select the center, and then you will, let's say, add another cube. And then merge it, extrude it this side, mirror extrude or something like that, and you will get one shape only, one shape. Okay. And then if I say now I want this model, so what are you going to do? You'll have to redesign this whole thing. Okay, you have to redesign. You cannot, like, you see, once you're done with this model, you cannot do anything to actually get this back again, unless you use back the same model and then you're going to cut off this part. Okay, you can use a pocket function to actually remove this. And suddenly when I say I want this, then from here, that is rather tedious. Okay, so you see you have 4 different models over here, which even if you want to actually move from this main model, it would involve quite complicated steps. Okay, so if you need to have multiple type of models over here, so the easy way out is to use Boolean operation, whereby you need to identify the basic shapes needed. So in this case, what is, for instance, if it was a 2D version, if I want to have this, and this, the basic shapes that I need would be like a circle and a square. So once I do that, when I design in CATIA, what I would do is, let's say first I draw a square, okay? And then next, usually you will select the surface to extrude the circle. But instead of selecting the surface, there will be an option in CATIA called insert body. That means you're inserting a new body. So in your model, when you draw, the usual CATIA you do, all this is considered as one body. Okay. In Boolean operation, each extrusion added is actually a different body. So it will be recognized as different parts. And it's not assembly, it's still design, but it's recognized as different parts. So once you have that, okay, then you can actually choose. There is an option called Boolean function in one of the drop-down toolbars, and you can start doing this. You can actually, have addition, difference, intersection, of which between each of this, you can select which is your main body base. All right. While I speak this, it's actually a lot clearer. Let me see whether I can show this video. Hang on. Okay, it doesn't matter if there is no sound because just now I didn't click the optimize, but okay, you see, now they're drawing something here. So I'm going to skip. Okay, so extruded. Sorry. Okay, now I want to add something, right? You see, they go to insert body. Then they select the surface. And then they draw the usual, okay, the circle, done, extrude. So you see here, in your model tree, you can see there are 2 parts, part body and body 2. Okay, so this is body 1, body 2. Okay. Now you can have different shapes. You see, you can hide either body. In your common design, you will not be able to do that. Okay. All right. Next, if you want to use the Boolean operation, they will go into let me fast forward it. So we're going to actually see this in the lab ourselves. Okay. So Boolean operation is a toolbar over here, which you can actually extract, and you can see. Under Boolean, they have add, they have remove, they have intersect. Okay. So let's just say you look at add as a function. So what are we adding? Okay, we are adding body to the part body, which is the main body. Okay. So once you preview, when you hide, you see it becomes the whole body now. Okay. Now if I move forward, they're going to do remove. So what they want to do, they want to remove body 2. Waiting for the video to move. Okay, so remove body 2 from the part body. When they click OK, you see this is what happens. Okay, so let me go back to. All right. So that's the concept of this Boolean operation. Back to. So therefore, the advantage is you can actually acquire different shapes with just 2 primitives design. Okay. Now, the actual advantage can be actually seen when you are combining rather impossible shapes, like, or in fact, shapes which you cannot design. For instance, you can see this is a helical spring, and this is designable in CATIA. You can actually model this. But can you model this? Can someone tell me, can the human skull, the head over here, can it be modeled? Anyone? Are you all there? Okay. Are you all there?
Yeah.
Can the
Yes,
human
yes, yes,
skull,
yes.
okay, can the human head be modeled? The one I showed just now.
Yes. I think can.
Can?
I also think
No.
Okay, some say can, some say no. I don't know, one said no. For those who say can you tell me how you'll do it?
In surface tu,
Sorry?
guna surface.
Okay, guna surface. All right, fine. Boleh guna surface. But the question here is, how are you going to get all this calculation, the curve of the head, the dent of the eye, you know, this, you understand? All the fine curves. They
Oh,
which are literally uneven, you know, if you ask me. There is no, it's not like a circle where it's, you know, the equal radius. The radius of our head also is not equal, right?
right. Yes.
Okay. So I'll give you the answer. To model this, it's not possible. Of course, you can model, but to get it accurately according to this particular head, like I said, model my head, you will not be able to model it accurately. You can only make estimations as you go. Okay. But one way to actually do this is later you learn, the later part of the chapter, is you can reverse engineer this entire model. That means you can scan the image of the head and bring it into CATIA through digitalization, and you can actually recreate back the surface and then create the solid. So usually for what we call organic shapes, we call them organic because they are more natural occurring shapes around us, right? In engineering, of course, we use this in biomedical studies, you know, where our body, our bone, you know, dental studies, implants and all this, they are organic shapes, very, very different shapes for different people. So this kind of shapes, they actually use reverse engineering to bring it. And when you want to cross combine, right? Design the models and organic shapes like this. If you want to get this, this, and this, it's impossible. You can actually model it, but you need to use the Boolean operation. So Boolean operation can actually create what we call all this odd or interesting shapes. Okay. Apart from that, its functionality is such that you can just use minimum primitives and maximize the variation of design. Okay. But you must know how to actually use it. So this is the advantage of Boolean. So here you can see, you know, you have a block cylinder. We saw this in the video just now. So how the concept of Boolean works is, it cuts off boundary to boundary. So you have a circle, you have a square. Okay, so if you want to add, unite, intersect, remove, it will actually detect boundary to boundary and make the what we call the removal or the intersection whatsoever. So this is what we call the CSG tree, or constructive solid geometry tree. Okay, so sometimes you may get exam questions based on this, stuff like that, where, you know, if you're given an image, all right, a final image, so you'll be asked, how did you construct this through the constructive solid geometry? So how do you actually construct this? You will have to have your base block. Okay, so like you see the first base block, and then you have the next block, the bottom block, which you actually unite to bring the bottom block. Then you have a cylinder, you subtract. Then you have a wedge over here, which you subtract, and then two cylinders, which you subtract. So therefore, you will get the final shape. So these are the operations. What are the shapes used to actually reach this final shape? Okay. So basically, it's a binary tree consisting of geometrical primitives, transformation, and symbols representing Boolean operators. So CSG method enables one to build the complex shapes quickly, but only within limitations of the sets of primitive available. So let's say you have a cylinder, all right, and you have a square, and then only with this limitation, you can actually make a cross match. So it depends on how many things you bring in to actually use your Boolean operator. Okay. The next type of modeling is boundary representation. So the boundary rep, okay, is a model such where you actually build model based on, okay, based on the name itself, boundaries. Okay, so you actually have boundaries connected by vertex. Vertex means points. Okay, and once your base boundary is built, then you actually build other boundaries connecting them by, again, edges. Okay, so the geometry of an object is described by its boundary, namely vertices, edges, and finally surfaces. Okay, so this is a BREP model. So basically what you do is you draw, let's say, the base, and then you extrapolate based on the surface. So most of the commercial solid modelers are actually boundary rep types. So you should understand CATIA uses boundary representation. So does SolidWorks, so does many other things, because in Boolean, you have to have a different type of design. So what are you all doing? When I say draw this box, you all first draw a square, and then you will extrude. Okay. Okay. However, Boolean representation is always there in most of the BREP modelers. Okay. So the application of solid model, we don't have to go through this. This is many. Number one, obviously, you can visualize, you can calculate the mechanical properties, right? You can use assembly modeling to identify problems in assembly. You can do drafting. And because you get a CAD model generated, you can do rapid prototyping. You can analyze the structure, the motion of mechanism through DMU, digital mockup unit. Then you can analyze through design. You can actually program your numerical codes for machining, robotic simulation, etc. Okay, so this was a repetitive. Okay, this one I will cover based on easier. Okay, right. Last part is hybrid modeling. So what is hybrid modeling? Remember this one I showed you earlier. This, okay, when we want to actually bring in complex organic shapes or shapes that you can't actually design, then we use the hybrid modeling concept, which actually combines digital shape sampling and processing with the power of CAD to provide innovative solutions, right, for parametric reverse engineering. So we actually reverse engineer certain parts. It uses the digital shape sampling and processing method where you can convert 3D scan data. Okay, so what it does is, let's say you put a skull over there, it will, you scan the entire skull, and as it scans, it actually picks up points, so it forms like how we would say like a cloud of network of points, right, into digital model. So once it does that, then it will actually, you can import those points and it will stitch. So the more the points, all right, the more accurate the surface that you're building in, all right. So you can bring it into digital models, and then once you bring the model in, then you can stitch the surface and then the volume, the solid, and then you can use it for analysis, right? So you can actually visualize, analyze, manufacture, and everything. So combining advantages of digital shape sampling and processing, all right? Once you bring that in, you can actually remodel the part. So when I asked you, could you actually model the skull? We can't, right? But once you bring this in, imagine you actually have a hat shape of your head, and you can start testing what happens to the structure. The traditional CAD works well when you model from sketch, but there's a limitation when it's difficult to reconstruct complex shapes. So therefore, hybrid modeling fixes this limitation. So it's usually used a lot in your postgraduate studies. Okay. So when you want to reconstruct something that difficult, obviously it's not easy to actually reconstruct. So therefore, what you need to do is you need to bring in the digital model. And once you scan it in, which is only done in 1 to 2 days, even less, then that's it. It becomes like your CAD model. So the application is you can capture. Yeah, my mouse keeps disappearing. Okay, change the. Okay, you can capture physical designs and prototypes. You can reproduce legacy parts, parts of, legacy parts which may not have any CAD model data or drafting data. Then you can actually just take the part and you can digitize it and remodel it. You can replicate complex shapes, organic shapes, like I mentioned. Prepare as build models for CE application. This is used in how do we know how much our bone can tolerate, what kind of implant to put in our bones and everything. We are using this hybrid modeling. Enable mass customization of unique components, right? Like dental application and all those things. And we can preserve historical and cultural artifacts because they don't have any CAD data, and we can just redesign them, reverse engineer them, and redesign them. So this is an example, right? So you see you have an impeller over here, which is pretty complicated in shape. So we scan the image, and once you scan, what is common and will happen usually is you can see over here, this yellow area, these are all what we call missing surfaces. So this is bound to happen. So when that happens, what we do is we actually stitch the surface up. How do we stitch the surface up? You remember we learned surface, right? So you see through the outline of the surface, we outline the surface, and then what we do is we actually, like what I'm doing right now is I'm coloring, this area here. So like this, we extrude the surface along this boundary. So it's like, covering. You extrude and cover. Okay, basically superimpose the surface with its boundaries. Like let's say if I ask you to draw, let's say a cylinder, let's say I draw a cube here. Okay, then I say draw a cylinder up to here. Okay, so what you would do, you would select, let's say, a surface over here. Let's say there's a plane. Okay, and then when you extrude, you would extrude all the way in. So you go, tembus, it will actually penetrate through your solid. Similarly, we actually extrude past this boundary. Okay, so we stitch. Once we are done with that, okay, and then we trim any excess, and then we get a clean covered shape. So when every surface is fully covered, then only we can analyze, because when you want to do finite element analysis, we want to do meshing. It should not have any hollow emptiness anywhere. Okay, then we can use these parts for analysis. So the advantages, okay, of hybrid modeling, similar to the application, it uses 3D investment. Basically, it uses your CAD modeling system where you bring in your reverse engineered product and you can take it from there, move forward with any other innovation you want to do with it. It helps to quickly create new designs, especially complex ones. Okay, and the advantage, right? It's hours opposed to days or weeks if you're going to redesign. Produce native parametric CAD geometry. So for whichever parts that you do not have any CAD geometry for it, we can actually create it. Generates accurate result. As I said, if you wanted to model the skull, the head, all right, see, it will simply not be accurate because we don't know the curvature. But when you reverse engineer, digital shape sample the part, all right, 3D scan it, you will get the exact shape. Okay, so you won't have any data loss. Okay, so that would be all. Do I have any questions from you all? So this is the first portion of chapter 4. The second portion will be actually the calculation. So far, any questions?
So far, no.
No.
Okay, Anna. Right, let me stop sharing. Recording.